ladies and gentlemen.
Let's talk solving linear equations. So a linear relationship is a relationship between variables and numbers where all of the variables present are raised to the first power and the first power only. No powers of 2, no powers of 3, no powers of half, only powers of 1. So if I solve, or we solve, a linear equation where we have one variable only, we will have three possibilities for answers. We will have either only one answer that works, we will have no answers work at all, or it does not matter what the value of the variable is, it will always work, and we call that an identity. So when we solve these equations, we're solving according to a balance beam. We have to make sure that whatever we're doing to one side, we're doing to the other in order to maintain this balance, unless we're simplifying, and that doesn't change the value. So we can do this in two major ways. That is by adding the same thing to both sides of the balance. If I add 4 to one and I add 4 to the other, it maintains balance. Or multiplication. If I multiply one side by 2 and multiplies the other side by 2, it also maintains the balance. Keep in mind that subtraction is just negative addition and division is multiplying by a reciprocal. So let's get started. Question 1. We're going to solve for x. So we have this 4 times a quantity x minus 3 plus 2 equals 5x minus 7. Now keep in mind, there's more than one way to solve an equation. You don't have to follow it exactly like I am. So if your way works and you get the exact same answer, that's awesome. Do that, whatever makes most sense to you. I'm going to go about it in a way that makes most sense to me. So first and foremost, I see that I have parentheses. And I know that the parentheses are there because the entire thing, the x minus 3 itself, is being multiplied by 4. So I'm going to distribute that multiplication. So 4 times x is 4x. 4 times negative 3 is negative 12. And then I have this plus 2 equals 5x minus 7. Now I just got done saying that we have to maintain balance on both sides. If I do something to one side, I've got to do something to the other. Well, if we simplify, we're not actually changing the value, and therefore we don't need to move anything on the scale. We can do a little bit more simplification because we have this minus 12 and this plus 2. Minus negative 12 plus 2 is negative 10. So we have 4x minus 10 is equal to 5x minus 7. Now personally, I like to keep my variables as positive as possible. So for me, I'm going to take away 4 x's from both sides. And I'm doing that in an effort to keep my x's positive. I could take away 5x, but I'd end up with a negative x on the left. This way I get a positive x on the right, and I'm a little bit happier about it. So this cancels. 4x take away 4x, 0. And then 5x take away 4x leaves me with 1x, or just x. And I can also move other parts of the equation at the same time, in the same step, if you will. Since I'm getting the variable alone on the right-hand side, I need to move the negative 7 away. So if I have minus 7, I can undo minus 7 with a plus 7. It's its opposite. Minus 7 plus 7 is 0. That cancels. Negative 10 plus 7 is negative 3. So x in this case is negative 3. And if you don't like the variable being on the right at the end, you can always flip your equation and write it as x equals negative 3. No problems there. What if I increase the difficulty? So for this equation here, we're solving for w, and we have a fraction is equal to a fraction. So how do we go about this? Because everyone loves fractions. Well, they're not as scary as they seem, especially if we think of a strategy to try to eliminate the fractions as early as possible. And one method to do that is multiplying by the least common denominator. How do we find that? Well, we break apart the factors of the denominator, and we multiply all of the unique factors together. So we have 4 here. Its factors are 2 and 2. 5 is prime, so its only factor is itself. So they have no common factors between them. They're all unique. So 2 times 2 times 5, well, that's 20. So we're going to multiply both sides of the equation by 20. Before I go ahead and start multiplying that in, I'm going to make life a little bit easier for myself. We have this divide by 4 on the left, and we have this divide by 5 on the right. We can apply that to the 20 now. So 20 times 4, or 20 divided by 4 is 5. Now all of these parentheses might get a little confusing, but we're going to take it from inside to outside so it's not as bad. And then over here, 20 divided by 5 is 4. And again, we get lots and lots of parentheses, but we're going to clean those up from inside to outside. And I just messed that up. They're a little tricky, even for me. So, as I implied, we're going to clean up the parentheses from inside to outside. Do keep in mind that variables and numbers don't mix. I can't say that w plus 1 is 2w because 1's not a w. So, in order to clean this up, we're going to distribute this 3. Those are the reasons why the parentheses are there. So, we're going to get rid of those parentheses by multiplying. 3 times w is 3w. 3 times plus 1, or positive 1, is plus 3. And then we have that minus 2. Now these outer parentheses still exist because of the 5. We're also going to clean up the other side a little bit. So we have these parentheses in here. Why do those parentheses exist? Those parentheses exist because of this minus. It's like a minus 1, if you will. And we're going to distribute that as well. Minus positive 2 is just minus 2. Minus negative w is plus w. And then everything else stays the same. Oh, I'm mixing up my colors. It is fine. Now, we're going to simplify the insides of the parentheses. If we have any like terms, we're going to combine them. And we do. We have some on both. We have this plus 3 and this minus 2, which makes a 1. Nothing in common with the w. So that stays. And here we have this 5 minus 2, which turns into a 3. Nothing for the w, so that stays the same. Now, why do these parentheses exist? Well, the ones on the left exist because of the 5. Ones on the right exist because of the 4, so we're going to distribute that now. So 5 times 3w and 5 times 1. Well, 5 times 3w is 15w. 5 times 1 is 5, so a plus 5 there, equals, and then we'll do 4 times 3, which is 12, and 4 times w, which is a positive 4w. Just like in the last one, I try to keep my variables positive, so I am going to strategically subtract 4w from both sides. And since I'm moving my w's to the left-hand side, I'm going to move my numbers to the right. So I'm going to undo this plus 5 with a minus 5. Always the opposite. So these w's cancel and these 5's cancel. And that leaves me with 11w is equal to, well, 12 minus 5 is 7. We can finish this off. How do I get rid of the multiplication by 11 that's happening to the w? We can divide. So we divide both sides by 11. And we get w is equal to 7/11. It is a-okay to have fractions as answers. You can always make them mixed numbers or decimals, but I find leaving them as just regular fractions or improper fractions is the easiest thing to do. That is it for that one. So not as bad as it seems. There's a lot of work there, but it's not difficult. A lot of it's just the same process, just simplifying as much as you can. Then what can we clean up? What can we move? So on and so forth. All right, for this one, it's a little bit different because we have two variables. We're solving for x still, which means that we're going to get the x alone and everything else on the other side, but we have x's and y's. So our final answer is going to not be a number, it's going to be x is equal to an expression containing numbers and y's. So let's do it, shall we? Well, first and foremost, we have all these parentheses. Why do the parentheses exist? They exist because of the multiplications we have, so we're going to distribute. 2 times x is 2x, 2 times y is 2y. Both of those are positive. And then 5 times x is 5x, 5 times y is 5y. And both of those are positive, so pluses between everything. Now, again, I like to keep the variable I'm solving for positive, so I'm going to subtract 2x from both sides so that I end up with a positive 3 on the right. This would be positive 3x. And in the same step, I'm going to move the y's to the left-hand side. So I am going to subtract 5y, subtract 5y, cancels out on the right, but on the left, we have 2y minus 5y, so we have negative 3y. And to get the x alone, to isolate it, we can divide by 3, divide by 3. So we get the expression, the final expression, as x is equal to negative y. That's an awful looking equals negative y. Now, if we had numbers on that, that's still fine. As long as the x is alone, no x is on the other side, that's all we need to do. What about this one? More fractions. Well, what was the strategy to simplify the other one? The least common denominator. Well, let's look at the denominators of everything. We have denominators of 3, 5, and 5. If you have a whole number, remember the denominator is 1. So for our intents and purposes, we're not really going to count it. So what is the unique factors here? We have a 3 and a 5. And that's it for unique factors. 3 times 5 is 15. So we're going to multiply both sides of this equation by 15. In order to multiply, we're going to distribute. 15 times 2/3 x is 15 divided by 3, which is 5 times 2, which is 10x. And then 15 divided by 5, which is 3, times negative 3 would be negative 9. Same way over here, we're going to distribute here. 15 times 2 is 30. And then 15 times negative 1/5 x is 15 divided by 5, which is 3, times negative 1, negative 3x. Again, I like to keep it positive, so I'm going to move all of my x's to one side and try to make it so that my x's are positive. I can do that by adding 3x to both sides. And since it seems I'm moving my x's to the left, I'm going to move my numbers to the right. I'm going to do that in the same step. I'm just going to add 9, and these cancel. That leaves us with 13x is equal to 39. How do we simplify? We divide by 13. Divide by 13. So x is equal to 3. Not that bad. Now, all of these had one solution, or the solution was in expression. Here, we're thinking about how can I make it so my equation has infinitely many solutions? Well, for us, that means that we have the same exact equation on the left-hand side and the right-hand side. We have an identity, so it doesn't matter what we plug in. If we think of some identities, well, the easiest one would be x is equal to x. It doesn't matter what I plug in. That's always going to be a true statement, right? But also, wouldn't it make sense that x plus 1 is equal to x plus 1? Also doesn't matter what you plug in. That's also a true statement. What about 2x is equal to 2x? Also the same, right? What if I combine those two last ones together and I get 2x plus 1 is equal to 2x plus 1? It still doesn't matter. So it doesn't matter if we have multiplication or addition happening on either side. As long as both sides are the same, we will have infinitely many solutions. So let's look at what's in common here. I already see that I have a -1 and a -1 in common, so I'm not really going to care about that. I have an AY and a 7y. What value of A makes it infinitely many solutions? What value of A makes it mirror the other side? That's a common sense question. That's A is equal to 7. You don't really have to solve that one if you think it through. You may have to simplify sometimes, depending on the question. If you have a question like this in the future, you might have to simplify one side so they look the same and then compare the parts you want to be the same from there. So keep in mind, it's not always going to be just that. It could be a little bit more complicated. Now here's more of a standardized test question. If 7x plus 14y is equal to 42, what is the value of x plus 2y? Quite commonly on standardized tests, you're not solving for a specific variable. You might be solving for a combination thereof of variables. In this case, a combination of x and 2y. So what you need to keep an eye out for is, can I turn what I have into what I need it to be? Which in this case, it looks like so. 7 and 14, 1 and 2, the relationship is 14 is double 7, 2 is double 1. So looks like this one is just 7 times larger. And since it's 7 times larger, let's just divide both sides by 7. If I do that, I distribute the division. So 7x divided by 7 is, it's no longer 7, it's just x. And then positive 14y divided by 7 is a positive 2y. 42 divided by 7 is 6. So what is the value of x plus 2y? 6. Not that bad, right? Here's a similar question. So in this case, we have 5q minus 7z is equal to 5z minus 7q. And we want to find the difference between q and z. Again, we don't care about what they equal themselves, just the relationship between them. So I notice here that q is positive and z is negative. So I want to rearrange this equation so that stays true. And it looks like my q is positive here and my z is negative here. So I'm going to move everything to the left-hand side. So I'm going to subtract 5z, subtract 5z, and I'm going to add 7q, add 7q, and I get 12q minus 12z is equal to 0. What's the difference between what I have and what I need? Well, what I have is 12 times larger than what I need, so let's divide it by 12. We divide both sides by 12. We again distribute the division. 12q divided by 12 is just q. Negative 12z divided by 12 is just negative z. And then 0 divided by 12 is 0. So what is q minus z? It's just 0. So not too bad. If you have any questions, let me know. Otherwise, I'll see you in the next video.